Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. We are almost done writing the code for importing one or more images and constructing a texture from those, depending on various settings. Today we are going to look at how we can figure out if an image can be used as a normal map when we are trying to create a texture. We'll also write a function to decompress textures that are encoded using block compression. This is needed in order to be able to view the textures in the editor. I'll add a new CPP file for our normal identification code. Here we determine whether it's likely that a texture is a normal map. We'll do that by sampling the texture and examining the RGB values as if they were XYZ components of a vector. However, before spending any time on sampling pixels, we can already return false if the size of each pixel is anything other than 32 bits, or the RGB channels are not 8-bit. If the image format is one that can be used for normal maps, we are going to write a function that evaluates the image by sampling its pixels. To do so, it will need a sampling function, which we'll also have to write. However, because the image format could be BGR instead of RGB, we need two sampler functions, one for each RG and B ordering. We are going to do some calculations using the sampled color values. Therefore, I'll define a color class first and write basic operators like addition and multiplication. Let's start with helper functions that determine if a color is transparent or black. The addition operator returns the component-wise sum of two colors. We also need to be able to multiply and divide a color by a scalar value, so we define operators for that as well. Next, we write the sampler function, which should have this function signature. Here we have got a pointer to the byte position of a pixel within the texture, and we simply read 4 bytes from that location. Note that the bytes have an integer value between 0 and 255, and we need to convert it to a floating point value between 0 and 1. That's why we need to divide by 255. The BGR sampler is the same function, but the red and blue channels are swapped. Now we can sample the image and evaluate if it's likely to be a normal map. Let me first explain how this function determines if a texture is a normal map. Looking at this example, we see a texture that can be used as a normal map, but it doesn't look like a typical normal map. It has black as well as transparent areas, and some parts of it have colors which we don't often see in a normal map. To decide whether or not this texture can be used as a normal map, We first sample a grid of pixels evenly distributed over the entire texture. In order to do this analysis as quickly as possible, we don't sample every pixel, but a maximum of 4000 pixels. This is a random value that you can choose freely. Since the normal map is allowed to have transparent as well as black pixels, we are going to ignore any samples that are taken from those areas. The samples that aren't transparent and do have a color value are then treated as 3D vectors. We can calculate the length of each vector. We know that normal vectors have a unit length, so we can test if the length of each sampled vector is larger than some threshold value. We set this threshold a bit lower than 1 because sometimes the length of normal vectors is not exactly 1 depending on the software that was used to generate the normal map. If the vector's length is larger than this threshold, we count the sampled pixel as an accepted sample. Moreover, we'll accumulate the color of all accepted pixels in order to compute the average vector length later on. If the sampled vector length is less than the threshold, we'll count it as a rejected sample. After we are done sampling, we check if the number of accepted samples is high enough. For example, we can decide that at least 25% of all sampled pixels should be accepted. In that case, we can calculate the ratio of rejected versus accepted pixels. If this ratio is about some threshold, we conclude that the texture is probably not a normal map. Finally, we calculate the average length of all accepted samples, and if this is within a certain range, then the texture is likely to be a normal map. We start by defining the sample count and sample interval, which depends on image size as well as the sample count. Note that here the image size is given in bytes, so sample interval is always a multiple of 4. If the image is not big enough for this many samples, we'll try to sample every pixel. The minimum number of samples that must be accepted is 25% of all samples. Again, this is something we can choose freely. Next, we initialize the accepted and rejected pixel counts and the average color. A sampler function is then called to get the color of the pixel at each interval within the pixel buffer. We use a function to evaluate the color of the pixel, which returns a negative number if the pixel is rejected, and a positive number if it's accepted. The pixel is ignored otherwise. We'll write this function in a minute. When the pixel is rejected, we increase the rejected samples count by 1. If it's accepted, the value of accepted samples is incremented by 1. We also add its color to the average color. As I mentioned before, we ignore pixels that are transparent or black. In that case, evaluate color will return 0. Otherwise, the color is converted to a normal vector with components that have a range between -1 and 1. Then we compute the length squared of this vector. We use the length squared so that we can avoid calling the square root function. If the z component is negative or the length squared is less than some threshold, the pixel will be rejected by returning -1. Otherwise, it's accepted. Now let's define our threshold values. The average length of all accepted pixels should be larger than 0.7. For each sample to be accepted, its length squared should be larger than the square of this value. Note that with this value, the test for average vector length will always pass, because all accepted vectors have at least this length. However, we can choose a different value to make different parts of our test more or less strict. If we have got enough accepted samples, we calculate the rejection ratio, which, if larger than some threshold, will tell us that the texture is not a normal map. For example, less than a third of all pixels may be rejected. Finally, the average length of all accepted pixels is calculated. We can check if this value is within a certain range. In addition, we also look at the average z component to see if it's pointing away from the surface sufficiently. This is all we have to do in order to make a guess about whether or not a texture is a normal map. The last function for today is decompress mipmaps function. We only need this in order to be able to view a block compressed texture in the editor. First, we make sure that this is actually a compressed texture. Then we need to read the images that make up the texture. Therefore, I'm going to write a new function that will take the texture data and return an array of images. Here we check that we have a valid data pointer, data size, mipmap levels, and array size. In order to read the images, we first need to know how many of them we should read. For 2D textures, this is simply the array size multiplied by mip levels. However, for 3D textures, each mip level has a different number of slices. So depending on the top level depth of the texture and the number of mip levels, we can end up with different number of images. We are using the array size in texture info for either the array size when the texture is a 2D array or a cube map, or the depth value when it's a 3D texture. Therefore, we can use it to calculate the number of images for 3D textures. As I mentioned, the image count for 2D textures is array size times the number of mip levels. we'll use a blob stream reader to read this many images from sub-resource data. Note that we already created an array that has enough room for all images, so we don't have to call pushback function. At the end, we return the array of images. Before decompressing these images, we need to fill in the metadata. We can find everything we need in texture info. Note that the array size for 3D textures is always 1, since there is no such thing as a 3D texture array. On the other hand, the depth for 2D textures is always 1. I still need to properly handle the case for 1D textures. Right now we don't have anything that can indicate whether a texture is one-dimensional or it's a 2D texture with a height of 1 pixel. Now we can call DirectX text decompress function. Note that we passed the XGI format unknown, because we want this function to return something that matches the BC format of the input data. For example, when we call it to decompress a BC4 texture, it will return a texture with a single channel format. If decompression succeeded, we copy the results back to texture data and set texture info accordingly. Otherwise, we set the error code and return. Let me fix a typo here. This cast is unnecessary. Make better comments here. This should be image width and image height, because we are examining the images within a source with multiple images. This can be U32. Do a little formatting. And we are done. This code should do pretty much everything we want in order to import textures. Something that I get asked from the viewers every now and then is that I show the results at the end of each video. Unfortunately, that's not always possible. As you can see, although we finished this code, we can't use it right now because it's intended for use with the editor. So first we need to enable the editor to call this code so that it can do something useful. In the next episode, we are going to do a bit of code cleanup for what we have done so far. Then we'll start writing the editor code for importing textures. Thank you so much as always for joining me, and I'll see you next time. Thanks for watching. If you like this video, please feel free to like and subscribe. If you join me on Patreon, you'll get access to the code on GitHub, so you don't have to type everything over from the video. Plus, there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering!